So you can, if you think about this change of coordinates, so you don't change the spatial or the functions that define the field. What you change is the coordinate in this reference space. So this somehow amount at changing the measure as you change your hyperparameters. So you change the a priori that you have when you change the hyperparameters. Okay, is that clear? So here is a typical example where we have this Gaussian type covariance function. So it's the covariance between the 2-point covariance is decaying exponentially as a function of the square of the distance between the 2 points. And you have a parameter which is the correlation length. Okay. So here you have plotted different kernels for increasing value of the correlation length. And you have also in black another covariance which correspond to the average of all the other one with respect to h. Okay, so this is the average covariance for all the value of the correlation length. Correlation length here is assumed to be uniformly distributed between 0.1 and 1. Okay. Now, what you have here is a convergence of the spectrum. So I'm plotting the lambda k for different values of L hat, which is the correlation length. So you see that for a very long correlation, or say correlation of 1, you have a fast decay, while when the correlation is decreasing, you need more mode to reach certain convergence of your expansion. Okay? What you have in blue here, it's a case, no, sorry, it's a black here. It's the decomposition or the spectrum of the average covariance function. Okay? Now, we can do this change of variables by considering different reference bases that can correspond to this particular value of the correlation length, that you use as a reference basis, or the space spanned by the Ingot mode of the average covariance. And here is the convergence of the error as a function of the actual value of the parameter, hyperparameter L. So what we do is that we fix the actual value of the parameter L, and we see what is the error that is committed by approximating it into the reference basis. Okay. And you see that if I'm using a reference basis with a correlation length of 1, I have a great error till the process are actually a correlation length that is getting close to L equal 1. Okay. On the contrary, if I'm using a correlation length of 0.1 to build my reference basis, it's very accurate for all of the correlation lengths, but you see that the error remains quite, doesn't go to 0, because here we are using a fixed number of modes in the expansion. Okay. And the case of the average covariance is given here. You see that it is something intermediate. It doesn't do so bad for short correlation, but it doesn't go very well for long correlation, but on average, this is the best choice by definition. And this is also what you can observe here. When you increase the size of the reference basis, you see the convergence. And in the case where the covariance or the reference covariance is the average one, you have always the best error. Okay. And this case is the error average over all possible value of the correlation length. Okay. So clearly the takeaway here is that if you want to pick a particular reference basis, you should pick the one that is built on the average covariance. Not average correlation length, but average covariance. And by the way, if you at this, if you average with respect to L, you end up with a covariance that is no more Gaussian. Just as a side note. Okay, I'm going to skip here just to show the evolution of the modes when you change L. So this is the phi k of L. And I just want to point to an issue here, is that it can be very difficult to actually come up with a basis. Well, if you select the reference correlation length too large, you can have a very fast convergence, so that numerically, the higher order modes are noise, essentially, because the associated eigenvalue are 0, and you're not able to properly define smooth mode. And this is what you have here. It's just noisy things, because as L is getting larger, you try to project things on bases that are completely noisy. So there's some care to take when you do this change of base. Okay. Now, we have to sample this, and we have now, say, a common representation for all value of the hyperparameter in terms of a single set of coordinates that are the reference coordinate Q. So when you change the hyperparameter, you change the a priori measure on Q, okay, but you keep the basis. So you can keep the same value of Q when you sample. This is what we wanted to achieve. However, you still have to evaluate the log likelihood, the likelihood of the observation, which means that you have to evaluate your model for this particular value of Q and hyperparameter. Okay. So this can be very costly, as it has been discussed in previous presentations. So we want to rely on polynomial surrogates. This has been proposed by Youssef and Najim in 2004, 08, I don't remember. 9? Okay, let's be accurate, 9.5. And the key idea here was to construct a polynomial expansion in terms of not only the coordinates, but also the hyperparameters. Okay. One issue you have with this expansion is that if you have many hyperparameters, then the dimension of this input space become larger and larger, so you need more and more complicated polynomial expansion, very long series in high dimensions, so you're losing efficiency. So what we are proposing here instead is to acknowledge the fact that Q, in our case, is somehow the same for all H, and in fact it will be a Q of H, so to say, because we're changing the measure. So we don't have to go through this, extended parametrization of the polynomial expansion. We can just use a single set of random variables. And of course, we will try to define this expansion in an optimal way with respect to a certain measures, minimizing some mean square error. And it will not be optimal for any value of H, but we are willing to drop this optimality consideration if it's going to be a good approximation for any value of H. Okay, so here just to illustrate what's going on in terms of change of variable to come up with a decent choice for the variable size that we are using to actually build the expansion, and the mapping between the coordinate size and their dependence on with Q and H here is expressed. Okay, so basically you construct again an expansion in terms of reference coordinates, and then you will exercise a change of variable or change of transformation of coordinates to evaluate a particular model value or surrogate model value using this expression here. Here just to show how this is converging when you're changing L. The takeaway is, again, use the average covariance to construct this space on this system of coordinates. This is the optimal one. And here's what we have actually now in terms of flowchart for sampling the problem. So first you have an offline stage where you select your reference covariance. You perform the KL decomposition, so this gives you reference eigenvalues and eigenvector that will be used to define the transformation, actually. Then you solve the polynomial chaos problem in that case to get the surrogate model of your model predictions. Okay, and now when this is ended, you enter the sampling stage where you propose values of the hyperparameters, coordinate, and noise intensity. This means that you prescribe a certain change of coordinate to re-express things in terms of the reference one. So this gives you a reference coordinate for the PC expansion. So you evaluate the PC expansion and you get the corresponding estimate of the model prediction. Using the noise label, you can compare this to the observation, so estimating the likelihood, and then multiplying by the prior, you get the posterior. Okay. So you see that this is highly reduced by reusing the surrogate model and reusing the decomposition to have the change of variable at this stage. So here's just convergence of the surrogate approximation as a function of the dimension of the reduction space and as a function of the polynomial order. And of course, you want to balance all this error. You don't want to be very accurate. This is what we have here. Increasing further k is not paying because we are here at a fixed polynomial degree. So here we are, in this part, we are dominated by the polynomial approximation, okay, or the polynomial approximation error, more exactly. While in this regime, there's no point of increasing k because, of increasing the polynomial degree because we are working with a set of reduced random variables that is just too small. Okay, so, and you want to balance these two errors. So let's try to apply this to learn two different types of functions. The first one is just a sin function, so very smooth, differentiable everywhere, C infinity, in fact. Second one is a step function, so very not smooth. And another one is actually a random profile sample from a Gaussian process with a particular correlation length, okay, just for the sake of the experiment. This is what you obtain if you don't use hyperparameters and instead assume a correlation length of 0.5 and a certain variability in your a priori and use 10 modes on a polynomial degree of degree 10. So in blue, you have the prior distribution. In red, you have the posterior distribution of the first 9 coordinates. Okay, and what you can observe is that you learn quite a bit for the 4 first coordinates. And starting from the 5th one, you're not learning anything. You can barely distinguish the prior and the posterior distributions. And here you cannot see even any difference. Okay? You have the KLD value, so the distance in terms of KLD. Now, if you use hyperparameters, this is what you obtain. And now you can see that you have significant differences up to mode 7. Okay, so now you much better learning simply by the fact that you're introducing some hyperparameter. So you can adjust your a priori and discover what is the best one. Okay. So you're improving your learning. And this is not surprising because this was for the case of the sine function. So it's very smooth. And here you can see the comparison between the different cases. So on top you have the case of a fixed covariance, and at the bottom is the hyperparameter. And what's interesting is to have a look to the case of the discontinuous field, and you see that it's not doing a good job because, of course, this is not in the a priori range. I mean, the a priori does not encompass processes that are discontinuous, because we have a smooth kernel. So it's not doing a good job, as we may have expected. But still, it is able here to find that the correlation length should be very, very small. Okay, so it's improving the mean distance, but it's certainly not a satisfying answer. Okay, and here you have a comparison of the posterior for the variance of the prior distribution and the a priori posterior and the correlation length of the a priori, the updated covariance length.